Hi there, Miss Barber here. We will wrap up our study of putting statistics to work with a lesson on statistical inference. The learning objectives for statistical inference are: be able to compute and interpret statistical significance, be able to compute and interpret margin of error, be able to compute and interpret confidence intervals, and finally, be able to conduct and interpret hypothesis testing. We'll begin with statistical significance. A set of measurements or observations in a statistical study is said to be statistically significant if it is unlikely to have occurred just by chance. Common levels of significance. We have at the 0.05 level. The probability of an observed difference occurring by chance is 1 in 20 or less. At the 0.01 level, the probability of an observed difference occurring by chance is 1 in 100 or less. Example: statistical events. Are the following events statistically significant? Explain. A. The Major League Baseball team with the worst win-loss record defeats the team with the best record. We would expect a team with poor win-loss record to lose most of its games. However, we also expect it to win occasionally, even against the team with the best record. This event is not statistically significant. B. In terms of global average temperature, the 16 years from 2001 to 2016 were 16 of the 17 hottest years on record since 1880. Analysis. Having 16 of the 17 hottest years on record occur in a single 16-year period is statistically significant. Indeed, having such a streak of hot years is very unlikely to have occurred by chance alone, and therefore provides significant evidence of a warming Earth. Example: statistical significance in experiments. A researcher conducts a double-blind experiment that tests whether a new herbal formula is effective in preventing colds. During a 3-month period, the 100 randomly selected people in a treatment group take the herbal formula, while the 100 randomly selected people in the control group take a placebo. The results show that 30 people in the treatment group get colds compared to 32 people in the control group. Can we conclude that the herbal formula is effective in preventing colds? Analysis. Whether a person gets a cold during any 3-month period depends on many unpredictable factors. Therefore, we should not expect the number of people with colds in any two groups of 100 people to be exactly the same. In this case, the difference between 30% the treatment group and 32% of the control group getting colds is small enough to be explained by chance. That is, the difference is not statistically significant, and we should not conclude that the treatment made any difference at all. Margin of error. Suppose you select a single sample of size n from a large population and measure its sample proportion. The margin of error for 95% confidence is E equals margin of error, which is approximately 1 divided by the square root of the size n. Confidence intervals. The 95% confidence interval is found by subtracting and adding the margin of error from the sample proportion. You can be 95% confident that the true population proportion lies within this interval. The margin of error decreases as the sample size increases. We write this as open parentheses, sample proportion denoted by p hat minus e for the margin of error, comma, p hat plus e. Example: unemployment rate. Suppose the Bureau of Labor Statistics finds 3,420 unemployed people in a sample of n equals 60,000 people. Estimate the population unemployment rate and give a 95% confidence interval. Solution. We first compute the sample proportion. So that would be the 3,420 of the people selected from a sample of 60,000. That is equal to 0.057, and E, the margin of error, is 1 over the square root of n, which would be 1 over the square root of 60,000. Using your calculator, we compute that is approximately 0.004. So, the confidence interval would be 0.057 minus 0.004, comma, 0.057 plus 0.004, and that computes to 0.053, comma, 0.061. What does that mean? It means that the unemployment rate is somewhere between 5.3% and 6.1% with a 95% confidence level. Hypothesis testing. The null hypothesis, denoted uppercase H subscript naught, claims a specific value for a population parameter. It is often the value expected in the case of no special effect. The null hypothesis takes the following form: null hypothesis H subscript naught, colon, population parameter equals claimed value. An alternative hypothesis, notation uppercase H subscript 1, is a claim that the population parameter has a value different from that claimed by the null hypothesis. Outcomes of a hypothesis test. 2 options. Option 1, reject the null hypothesis. That means we have sufficient evidence that supports the alternative hypothesis. And option 2, not reject the null hypothesis. That is, we lack sufficient evidence to support the alternative. Given the 2 options, we have 4 possible outcomes. One for the correct decision would be that the null hypothesis is false based on sample data, and we reject the null hypothesis. In that case, we have made a correct decision. Another correct decision is that the null hypothesis is not false based on the sample data, and we do not reject the hypothesis. We can also have 2 types of errors. Type 1 error is when the null hypothesis is not false based on the sample data, and we reject the null hypothesis anyway. And a type 2 error is when the null hypothesis is false based on sample data, and we do not reject the null hypothesis. Hypothesis test decisions. Compare the actual sample result, mean or proportion, to the result expected if the null hypothesis is true. If the chance of a sample result at least as extreme as the observed result is less than 1 in 100, test is significant at the 0.01 level. We have strong evidence to reject the null hypothesis. If the chance of a sample result at least as extreme as the observed result is less than 1 in 20, test is significant at the 0.05 level. We have moderate evidence to reject the null hypothesis. And finally, if the chance of a sample result at least as extreme as the observed result is greater than 1 in 20, test is not significant. We do not have sufficient evidence to reject the null hypothesis. Example, birth weight significance. A county health official believes that the mean birth weight of male babies at a local hospital is greater than the national average of 3.39 kilograms. A random sample of 145 male babies born at that hospital has a mean birth weight of 3.61 kilograms. Assuming that the mean birth weight of all male babies born at the hospital is the national average of 3.39 kilograms, a calculation shows that the probability of selecting a sample with a mean birth weight of at least 3.61 kilograms is 0.032. Formulate the null and alternative hypothesis, then discuss whether the sample provides evidence for rejecting or not rejecting the null hypothesis. The null hypothesis is always a statement of equality. Null hypothesis for us, mean birth weight is 3.39 kilos. The alternative is any difference being investigated. So the alternative hypothesis, that is that the mean birth weight is actually greater than 3.39 kilos. Under the assumption that the null hypothesis is true, the chance of observing a sample with a mean of at least 3.61 kilograms is 0.032. This is less than 0.05, but greater than 0.01. So the result is statistically significant at the 0.05 level, but not at the 0.01 level. Statistical significance at the 0.05 level provides moderate evidence for rejecting the null hypothesis, in which case the county official's claim would be supported.